Hello and welcome to the week 6 of the NOC 23 MA14 course Algebra 2 offered by NPTEL. So, I am one of the PMRF TAs for this course. My name is Shubhajit Dash, and today we'll be solving some problems based on the content of week 6. And I do hope that you are also attending Ajay Prajapati's sessions as well. Without much ado, we'll start. Okay, so this week you probably have learned about cyclotomic polynomials and composite extensions, Galois groups of composite extensions, and all those things. So we'll be doing problems based on all those things. So since Ajay Prajapati also already has solved the assignment 6, so I'll be solving. My problems are loosely based on those, but they are slightly different, so that you do get to learn something new. So the first question is again based on the assignment. So in the assignment you are asked to find out the 8th cyclotomic polynomial over Q, of course. Yeah, so I should write over Q. So now I am asking you to find the 10th cyclotomic polynomial over Q. Now this is very easy. If you have done the one for phi 8, then you already know what to do in the case of phi 10. So we quickly recall that cyclotomic polynomials were actually given by they also had an inductive definition. Firstly, they are defined to be polynomials. Yeah, sorry for the technical glitch. So yeah, so as I was saying that firstly phi, so the cyclotomic polynomials are defined to be polynomials over Q whose roots are precisely the nth primitive roots of unity, right? But we also know that cyclotomic polynomials are also given by an inductive definition. So we know that x to the power 10 minus 1, which is precisely the polynomial whose roots are all the 10th roots of unity, is the product over d dividing 10. So d is some positive divisor of 10 of all phi d x's, right? So we just quickly need to find out what phi 1x, phi 2x, phi 5x are, so that we can find what phi 10x will be. Okay. Now phi 1x is just x minus 1, the polynomial whose only root is a primitive 1th root of unity, which is just 1. Now phi 2x is equal to Uh, so what is phi 2x? Phi 2 of x is given by x plus 1. The only primitive second root of unity is minus 1. So this is phi 2x. And what is phi 5x? Phi 5x will be x to the power 4 plus x cube plus x square plus 1. Right? Since 5 is a prime, we already know what are the pth cyclotomic polynomials. So this is precisely phi 5 of x. Now, hence, we can say that phi 10x will be equal to x to the power 10 minus 1 divided by x minus 1 times x plus 1 times x to the power 4 plus x cube plus x square plus 1, and I leave it up to you to compute the rest of the result. Okay. So compute the polynomial. You just need to divide and nothing else. So this is the 10th cyclotomic polynomial. This is the formula for the 10th cyclotomic polynomial. Okay. So this is all for the first question. If you have any questions, please do write to me. This is my email ID, as you can see here. So we move on to the next problem. Okay. So we are given a natural number n. We need to compute what is the Galois group of q zeta n over q. Okay, where zeta n is a primitive nth root of unity. So we know that. So suppose we are working inside C. So we know what zeta n looks like, right? It's e to the power 2 pi I k by n, where k is greater than equal to 1, less than equal to n, and GCD of k comma n is exactly 1, right? So we know what zeta n is. It's a primitive nth root of unity, and we just need to compute the Galois group of this. Okay. Now we quickly recall, this was done in your class, that the degree of the extension q zeta n over q is precisely phi of n, where phi is Euler's phi function, and this is true because zeta n has minimal polynomial over q equal to polynomial over q equal to phi n of x, right? The nth cyclotomic polynomial is precisely the primitive, is precisely the minimal polynomial over q of zeta n, right? So we know that the degree of this extension is phi n, and we claim this, that the Galois group of q zeta n over q is isomorphic to Zn cross, right? Which is the group of units of the commutative ring Zn. So how do we prove this? So to prove this, we need to exhibit a map. So consider a mapping. We consider an arrow of sets, that is a mapping. So from gal q zeta n over q into Zn cross, given by, so any element in the Galois group is an automorphism of q zeta n, fixing q element wise or point wise. So sigma, take an element sigma. So take sigma is a morphism which is whose source and target are the same, and which is in fact an isomorphism. It's an endomorphism plus isomorphism, that is an automorphism. So we take sigma and we map sigma onto what? So observe that sigma, any sigma in the Galois group, is a mapping of q zeta n into q zeta n, and in fact onto q zeta n, since this is bijective, and it therefore sends zeta n to something, right? Now zeta n is an element, is a root of phi n, right? And since phi n has all its coefficients in q, more precisely in z, and since sigma is an automorphism of q zeta n fixing q pointwise, that means that sigma will permute the roots of phi n. So zeta n will be sent to some primitive nth root of unity, right? So it will be sent to some zeta n power l, right? Because zeta n, being a primitive nth root of unity, is basically a generator of the cyclic group of all nth roots of unity, right? So any primitive nth root of unity, in fact any nth root of unity will look like zeta n powers a, right? Power sum a. So we just take sigma and we map sigma so sigma map zeta n onto zeta n power a, and we just considered this particular mapping of the Galois group into Zn cross, which sends sigma onto a, right? So we need to pick a notation for a. So the notation that we are taking here is let's say, so sigma goes to, so this is just a notation, mind you. So log zeta n sigma of zeta n. Okay, so I will just write it down properly. I mean, write some note about the notation. So this is just a notation. Okay, so log of zeta n power sigma zeta n, how should I describe this? Okay, so maybe I'll write the class of this, right? Yeah, so log of zeta n sigma of zeta n is so yeah, I need to be precise about this. So okay, so is that integer between 1 and n minus 1. So it is that integer between 1 and n minus 1, right? such that sigma of zeta n. So it is that integer a such that sigma of zeta n is equal to zeta n power a. Yeah. Okay. Okay, so in fact we can say that integer between 1 and n such that this is true. And note that this is well defined because sigma of zeta n is some zeta n power something, some a, but a has to be relatively prime to n, right? Okay, so this is a well defined notation, right? Exactly. So zeta n power sigma of zeta n is zeta n power f for some unique integer between 1 and n which is relatively prime to n. This is always true, and that is why this notation is clearly well defined. And what else? And yeah, so this is my notation. So we check, so do check that the mapping is well defined. This is what I leave to you, and we can easily check that this is a homomorphism. Why? Because so we observe that so let's give a name for this mapping. Let's call this mapping F. This morphism is named to be F. This is a morphism of sets. Just I mean, right now where we exactly are, this is just a morphism of sets, but we'll show that this is a group homomorphism. So it's a morphism of groups as well. So we observe that F of sigma composed with tau is just log zeta n sigma composed with tau of zeta n, which is log zeta n sigma of tau zeta n. What is tau zeta n? Tau zeta n is precisely zeta n power log zeta n tau of zeta n. I hope that you are with me right now. So Zeta n power log zeta n of tau zeta n means that we know that this is that integer such that tau of zeta n is zeta n power that integer, right? So this makes sense. And yeah, so what now? So this is log of zeta n, sigma of zeta n power something. So, oops, sorry. Yeah, so this is log of zeta n, sigma of zeta n power log zeta n of tau zeta n. And what is this? This is zeta n power log of zeta n of sigma zeta n whole power log of zeta n tau of zeta n, right? And this is log zeta n power log zeta n sigma of zeta n times log of zeta n tau of zeta n. So what I mean by this right now is, therefore, which implies that f of sigma composed tau is just f sigma times f of tau, right? For all sigma and tau in the Galois group. In the Galois group of q zeta n over q, right? So f is a group morphism. It's a morphism in the category of groups from the group from the Galois group, from the group gal q zeta n over q to the group zn cross, right? And we also check that this map is injective, and then we'll be done. Okay, so okay, so this I leave to you. Check that this is actually a monomorphism. So check that f is injective. So do check this, that f is injective. Now since the cardinality of the Galois group of q zeta n over q, right, is equal to the degree of this extension q zeta n over is to q, right? Why? Precisely because this is a this is a Galois extension, right? This q zeta n over q, this extension is a Galois extension, and that is why we do have this, right? This is because q zeta n is a splitting field of the separable polynomial, let's say phi n x, or we can in fact take x to the power n minus 1 over q. So that is why this is a Galois extension, and hence, so as q zeta n over q is Galois, being as q zeta n is a splitting field of a separable polynomial over q, right? Right. So hence we can say cardinality of the Galois group of q zeta n over q is precisely phi n, which is also equal to the cardinality of zn cross, right? And thus we are done. So we already, why are we done right now? Because we already have exhibited, so the domain of the arrow and the codomain of the arrow are both finite sets, and we have that the arrow is an injection, right? The domain and codomain of the arrow, they are both finite sets of the same cardinality, and we have that the arrow is an injection, which means that this arrow f is also a surjection and hence a bijection. Since f is injective, hence f is bijective. Thus f is an isomorphism. of the Galois group of Q zeta n over Q into, and hence, and since it's an isomorphism, we can say onto Zn cross. Right? So this is an isomorphism, right? And thus we are done. So the Galois group of the nth cyclotomic extension over Q is precisely Zn cross. Okay. So let's move on to the next problem. If in case you have any questions, you can always write to me. Yeah. So let's move on to the next problem. So we are given a natural number n in n and we are taking a prime p. We just need to find out what are all the subfields of Fpn. Recall that the notation Fpn refers to the finite field of order p to the power n. Okay. Up to isomorphism, there is exactly one finite field of order p to the power n, and we denote it by Fpn. So we need to find out what are all the subfields of Fpn, right? So we recall again as usual that Fpn over Fp is just Zp, as we know, the prime subfield of the field of any field of characteristic p. So we recall that this is a Galois extension, right? Why is this a Galois extension? Because if we recall, then, and if we consider Fp and you consider the polynomial x to the power p to the power n minus x, then using the formal derivative test, you can check that this polynomial is a separable polynomial, right? You can check that this polynomial in Fpx is a separable polynomial, and Fp power n is a splitting field of this separable polynomial, right? So Fp power n, yeah, so what, so Fp power n is a splitting field of this separable polynomial over Fp, right? Which means that Fp power n over Fp is a Galois extension. And what is the Galois group of this extension? Also recall, this is also what you have covered previously, that the Galois group of the extension Fp power n over Fp is isomorphic to Zn, right? The Frobenius automorphism of Fpn being one of the generators of this Galois group, right? So the Frobenius map, which sends any a onto a to the power p, this is a mapping of Fp power n onto this is a mapping of Fp power n into itself. It is an automorphism and hence an element of the Galois group. So this is a generator of the Galois group, right? Yeah. So by the fundamental theorem of Galois theory, by the fundamental theorem of Galois theory, Fp power n, by the fundamental theorem of Galois theory, we know that the subgroups of the Galois group are in one-to-one correspondence with the intermediate subfields of the extension. Okay, so the subfields, or I should say the intermediate subfields, of this extension are in one-to-one correspondence with the subgroups of Zn. Now Zn is a cyclic group of order n, and we know that it's only, I mean, how should I phrase this? So yeah, so the only subgroups of Zn are cyclic groups of order d where d divides n, and there is exactly one subgroup of Zn of order d. Okay, there is exactly one subgroup of Zn of order d, and every subgroup of Zn is some cyclic group of order d. Okay, so we know that therefore the set of all subgroups of Zn are ZDs where d divides n, right? And hence we can find the intermediate subfields of this extension. Okay, so maybe I'll take some space. So the subgroups of Zn are, or maybe the collection of subgroups of Zn, the collection of subgroups of Zn are, I mean is the subgroup generated by D, or the class of D I should say, subgroup generated by the class of D, where uh, where where 1 less than equal to D less than equal to N, and D divides N, right? Yeah. So this is the collection of all subgroups of Zn. So what was I saying? Yeah. Hence, or maybe we can invoke the fundamental theorem of Galois theory once again. So we can say that hence we do know this, that uh, the hence the intermediate subfields of Fpn over Fp are, they are given by the fixed fields, right? Are uh, if p power n, so this is my e power h, right? That is a fixed field of the cyclic group generated by the class of D in the field Fpn, right? And where 1 less than equal to D less than equal to N, and D divides N, right? And if we want, we can actually sort of give a more concrete description of these subfields. So note that uh, yeah, so note that if p power n d is to Fp, right? What is this? This is equal to, so the degree of Fp power n, degree of this fixed field over Fp, right, is equal to, by the fundamental theorem of Galois theory again, this is equal to, so this is equal to Zn, the index of this subgroup in Zn, right? So what is the order of the subgroup generated by D? The order of the subgroup generated by D is precisely n by D, right? So the index is D, right? I hope I am not wrong here. Yeah, so D generates a subgroup. The order of the element of the class of D in Zn is n over D, right? And so the order of the subgroup generated by it is also n over D, and hence this index is n by D, which is D. So the degree of this extension is, so this is again, this equality is again by the fundamental theorem. Galois theory, right? So if p power n power this class of D, I mean this fixed field over Fp can be thought of as a, I mean, we know that one of the fact that Fp power n over Fp is a Galois extension is equivalent to saying that the base field Fp is equal to the fixed field of the Galois group of Fp power n over Fp in Fp power n, right? That is Fp power n power Zn, this is equal to Fp, right? So that this is equal to D, right? Yeah. Thus, if p power n I mean the fixed field of this subgroup, of the subgroup joined by class of D in Fp power n, is a finite field of order, finite field of order, since the index is, since the degree of this extension is D, so the dimension of this fixed field over the base field Fp is D as a vector space, which means that the cardinality of this vector space is P power D, right? So that Fp power n power class of D is just Fp power D, right? Thus the collection of intermediate subfields of Fp power n over Fp is this collection is equal to, that is, this collection is so maybe write it in the next line. I'll just write it in the next line. So this is equal to Fp power D such that 1 less than equal to D less than equal to n redivides n. Okay, so this is precisely the collection of all intermediate subfields. And finally, note that there is something extra that we have asked to find here. We need to find not just intermediate subfields of this extension Fp power n over Fp, but all subfields of Fp power n. But you do note this, that any subfield of Fp power n is actually an intermediate subfield of Fp power n over Fp, because any subfield of Fp power n contains one in particular, and since it will contain one, it will also contain the prime subfield Fp. So finally, note that any subfield K of Fp power n is an intermediate subfield of Fp power n over Fp, as K contains 1 and hence contains how should I say, it contains this collection 1, 2.1, 3.1 p minus 1.1, which is equal to Fp. Yeah, 0, 0, 1, 2.1, 3.1 up to p minus 1.1, which is Fp. Yeah. Right. So thus we have given a full classification of all the subfields of Fp power n. Okay, so that finishes this problem. If you have any questions, please do write to me. So let us move on to problem 4. So this is straightly taken from the assignment. I thought that this is an interesting problem, which is why we are discussing it. So I sort of changed the options, but the problem is the same. So we take K, L and F to be subfields of C such that F is contained in the intersection of K and L. We assume that K over F and L over F are finite Galois extensions such that the Galois group of K over F is non-abelian and simple, while the Galois group of L over F is abelian. Then we need to determine which of these options are correct. Okay, so we quickly do this. This is very easy. Okay, so first we recall a fact about Galois groups of composite extensions, that so this is just what we are using as a fact, that given this setup. Okay, so I'll just maybe I'll just say, let's see. Okay, so this was done in the video lectures, right? So I'll just write this: by the material from the video lectures, the automorphism group of KL over L is this is isomorphic to the automorphism group of K over K intersection L, right? And both are actually Galois extensions. I mean, KL over L is a Galois extension, and K over K intersection L is also a Galois extension. So this we know, and hence this later group is a subgroup of odd K over F, right? So that the former one can be thought of as a subgroup. There is an embedding or a monomorphism of odd KL over L into odd K over F, and yeah. So yeah, so there is a mapping of there is a morphism, that is a mapping of odd KL over L into odd K over F, right? We have a mapping, and this mapping turns out to be yeah, so we have a mapping of odd KL over L into odd K over F. We have a morphism of this of odd KL over L into odd K over F, right? And this mapping actually turns out to be injective. I mean, and we actually have an injective mapping. So odd KL over L can be thought of as a subgroup of odd K over L. This much is clear. There's no doubt about this. So now we just need to determine which of these options are correct. So the prime thing to tackle here is option B, which says that K intersection L is F. Okay, so this is what we are actually really interested in, and if we know that this is true or this is false, then we can actually conclude about option A and C. Okay, so let's just focus on B for the time being. Okay, so since odd K over K intersection L is a subgroup of odd yeah, how should I phrase this? So okay, so I'll just write this: since odd L over K intersection L is a subgroup of odd L over F, which is given to be abelian actually. Hence odd L over K intersection L is actually a normal subgroup of odd L over F, right? This we know, and as a result of which we also know, therefore, by the, so I'll just write why we know this. So this implies by the fundamental theorem of Galois theory, this implies that K intersection L over F, this extension is a Galois extension, which again implies by the fundamental theorem of Galois theory. Okay, by the same reason, this actually therefore implies that now we were looking so far in the Galois extension L over F. Now we apply the fundamental theorem of Galois theory to the Galois extension K over F. Now note that K over K intersection L is again, K intersection L is again an intermediate subfield of K over F, and since K intersection L over F is a Galois extension, Hence, the Galois group of K over K intersection L is a normal subgroup of the Galois group of K over F. Okay, so ought K in K over K intersection L, this is a normal subgroup of ought K over F, right? But this group was given to be simple, right? So which implies that ought K over K intersection L is either equal to ought K over F or K over K intersection L is equal to the trivial group. Okay. Now this possibility, this is not possible, as otherwise. What does this mean? Automorphism group of K over K intersection L is equal to the trivial group, which means this is a subgroup of K of automorphism group of K over F, which means that the subfield K intersection L is the largest possible intermediate subfield, right? Since the automorphism group, since the subgroup corresponding to the subfield K intersection L or the intermediate subfield K intersection L is the smallest subgroup of the Galois group, hence K intersection L has to be the largest possible intermediate subfield of K over F, right? Precisely because we know that the Galois extend, precisely because we know that. So what is the fundamental theorem of Galois theory all about? It says that you have two lattices, right? On one hand, you have the lattice of all subgroups of the Galois group, and on the other hand, you have the lattice of all intermediate subfields, right? And we know that the fundamental theorem of Galois theory basically says that there is a antitone Galois connection, right, from one onto the other, right? So the Galois connection is given by sending a subgroup H onto the fixed field of H in the extension field, that is E power H, and the inverse map is actually given by yeah, it should be precise. The Galois connection, so a Galois connection is a pair of maps in opposite directions, right? So the forward bijection is given by sending H onto E power H, while the backward bijection is given by sending any intermediate subfield B onto gal of E over B, right? This is what it says. So essentially what we have is a pair of adjoint functors between categories, right? These adjoint functors are actually, this pair of adjoint functors between categories which are actually lattices, posets actually, so that these are Galois this adjoint pair of functors is a Galois correspondence, and this the maps of this Galois correspondence, that is the functors, these maps are actually bijective, so that we say that we have a Galois connection between the two posets, right? So anyways, the point is that this Galois connection is an antitone Galois connection, which means that it's order reversing, right? So for corresponding to the smallest subgroup, you should have the largest intermediate subfield, right? So if automorphism group of K over K intersection L is the trivial group, then this would imply that K intersection L is equal to the largest possible subfield of the intermediate extension K over F, right? So this is K, which implies that K, oops, I'm sorry, I sort of confused between the two words. So a priori, what you have is, if you have, so this is the general setup. We don't need to discuss about this, but let me just be very precise here. So you have two posets A and B, and you take two I mean, you take two functors in opposite directions, right? So you take a functor from the poset A into the poset B, and you take a functor from the poset B into the poset A. And in fact, assume that these functors are actually contravariant functors, okay? So a functor between posets which is contravariant should be an order reversing map at the level of posets. Posets considered as categories. If you have contravariant functors from one such to another one, then that functor is just a set map, right? It's an order reversing map of the first poset into the second poset, right? So you take two order reversing maps in opposite directions, right? And this maps, that is this we were originally talking about functors, so we are taking contravariant functors in opposite directions, and we assume that these two functors in opposite directions form an adjoint pair of functors, that is there is an adjunction between these two functors, so that at the level of, so this was happening at the level of categories. So on so you have two categories which are actually posets, and you have two functors in opposite directions. Yeah, so you have two categories which are posets, you have two functors in opposite directions which form an adjoint pair of functors, right? So that at the level of sets, if you come down to the level of sets, what you have is you have two posets and you have to order reversing maps from one poset, you have to order reversing maps between them, and they form a Galois connection, okay? So the fact that the fact that at the level of categories, that is posets considered as categories and having functors from one category to another category, I mean, the fact that you originally started with categories, posets considered as categories, you had a functor from one poset into another poset which is contravariant, that is at the level of sets it was just an order reversing map from one poset to another poset, and you had a functor in the opposite direction from the second poset to the first poset which was also contravariant, that is it was another order reversing map from the second poset to the first poset. So you have a pair of functors in opposite directions, and we also assume that this pair of functors is an adjoint pair of functors, okay? There is an adjunction between these two functors, that is they form an adjoint pair of functors, so that at the level of posets what you have is a antitone Galois connection. Now these maps which are part of the data of this Galois connection, these maps are further assumed to be bijective and they are inverses of each other, okay? So assuming that they are bijective actually proves from the Galois connection property that they are inverses of each other, so that you actually have a Galois correspondence, okay? And the fundamental theorem of Galois theory is an example of a Galois correspondence, antitone Galois correspondence. So anyways, so this is not possible. If K intersection L is equal to K, then this would imply that K is actually contained in L, right? Oops. This would imply K is contained in L. Now why is that a contradiction? Why can't it be the case that K is actually contained in L? So K was assumed to be a, so what was K? Yeah, odd K over F was assumed to be non-abelian and simple, right? Yes, which implies this, which implies odd K over F. Okay, so which implies odd L over F, I mean L over K is a normal subgroup of odd L over F, as this was abelian, which implies that odd K over F, this is a Galois extension. Yeah, we don't even need this. We already know what K over F is a Galois, I mean K over F is a Galois extension. So odd L over K is certainly a normal subgroup. So, okay. So maybe I'll just erase that part or that step. So let me check if yeah, the recording is going on. So which implies odd K over F, which is isomorphic to a quotient object, right? It's isomorphic to a quotient object of odd L over F, that is isomorphic to odd L over F modulo odd L over K, right? Which is abelian. and this is a contradiction because auto k over f is non-abelian. Is non-abelian. Yeah, so that only the first case is possible. Thus, ought k over k intersection L is equal to ought k over L. I mean ought k over F, which implies that since the map sending an intermediate subfield onto the Galois group of E over B or K over B, any intermediates the map. So the map from the lattice of intermediate subfields to the lattice of subgroups, which sends any intermediate subfield B onto the Galois group of K over B. This map is bijective, in particular injective. So we have K intersection L must be equal to F. So certainly B is true, and since B is true, so B is true, B is correct. Hence A is, I mean option A. Hence A is correct as well. And finally option C says that KL over L is Galois, and this is clearly true. So C is also correct, as K over F is Galois. Implies, so K over F being Galois implies KL over L is Galois. This is always true. We don't even need the fact that L over F is Galois. Okay. But to deduce the fact that KL over F is Galois, we do need that L over F is Galois. So K over F being Galois and L over F being Galois will imply that their compositum KL over F is also Galois. But if you want to slide an extension one step up, so you are sliding the extension, Galois extension K over L along the extension L over F. You are sliding it. So sliding preserves Galois. I mean, preserves the fact that an extension is Galois. Yeah. So certainly C is correct. So A, B and C, all three are correct. So yeah, so this is problem 4. Okay. So we move on to the next problem. We need to find the Galois group of this polynomial x to the power 5 minus 4x plus 2 in Qx. Okay. Now this is the infamous Abel-Ruffini's quintic polynomial, which they sort of used to show that this polynomial, this is a quintic polynomial, this is not solvable by radicals. Okay. So one of the main aims of Galois theory is to prove the Galois great theorem, which sort of says, very roughly speaking, it says that if you take if you take a field of characteristic 0 and if you take a polynomial over that field, okay, then that particular polynomial is solvable by radicals. You know what solvability by radicals means, right? That is, there is some radical extension of the base field which contains a splitting field of this polynomial. So a polynomial is solvable by radicals if and only if its Galois group, that is a Galois group of the splitting field of this polynomial. The splitting field is an extension, and we only talk about Galois groups of extensions, right? So if and only if the if and only if the Galois group of the splitting field of this polynomial over the base field is a solvable group. Okay. Now they use this polynomial to show that the Galois group of this polynomial is S5, and we do know that S5 is not solvable as a group, so that this polynomial cannot be solvable by radicals. In other words, there can be no formula of the roots of this polynomial which involves the field operations of addition, subtraction, multiplication, division, and which involves only extraction of nth roots. Okay, there can be no such formula. Yeah. Yeah, so we just need to work out this particular polynomial. So, so observe that x to the power 5 minus 4x plus 2 is irreducible over q. By Eisenstein's criterion. So this polynomial is certainly irreducible over q by Eisenstein's criterion, and what do we know? Uh, so this is irreducible over q by Eisenstein's criterion, and so what else do we have here? Yeah. Okay, thus, okay, so we assume that let E over F be the splitting field over F. So let E be the splitting field over F of this polynomial x to the power 5 minus 4x plus 2 over Q, sorry. Let E be the splitting field over Q of this polynomial. Then 5 minus 4x plus 2 being irreducible is separable. Separable as Q being a field of characteristic 0 is a perfect field. So as Q is perfect, and which implies that E over F is a splitting field of which implies that E over F, or rather which implies that, more precisely, which implies that E is a splitting field of a, so which implies that E is the splitting field of a separable polynomial over Q, right? So E over Q is Galois, right? As E is the splitting field of a separable polynomial over Q. Okay, so we have that. So E over Q is Galois. Thus, the cardinality of the Galois group of E over Q, this is one of the equivalent conditions of a Galois extension. You should have a finite extension such that the order of the Galois group is equal to the degree of the extension. This is equal to this, and hence 5 divides the cardinality of the Galois group of E over Q. Now, why is this the case? This is simply because, so I'll just write down a note here explained in the video. So why is this the case? This is simply because 5, why does 5 divide the order of the Galois group? Because 5 divides the order of the degree. I mean 5 divides the degree of the extension. And why is that the case? So just take this polynomial x to the 5 minus 4x plus 2. Take any root alpha of this polynomial in E. Okay. Consider Q alpha over Q. Right. Since this polynomial is monic and irreducible, and alpha is alpha satisfies this polynomial. So this polynomial is a minimal polynomial of alpha over Q. Right. Hence the degree of Q alpha over Q is, which is equal to the degree of the minimal polynomial of alpha over Q, is 5, right? And by the Tower theorem, the degree of Q alpha over Q divides the degree of E over Q, so that 5 divides the degree of E over Q, and hence 5 divides the order of the Galois group. Also, so now we investigate the roots of this polynomial. the roots of this polynomial. So we just need to see whether this polynomial, or how many real roots does this polynomial have. Clearly x to the 5 minus 4x plus 2 has either one real root or three real roots, or five real roots. We just need to see which of this is correct. Okay, so we claim that this polynomial actually has three real roots. Okay. Or more than one real roots would suffice. I mean, less than five real roots would suffice. Yeah. So so a way to do this would be, so this polynomial has all distinct roots. This much is known to us, and we considered. So we call this polynomial equal to fx. We consider f prime x, which is 5x to the power 4 minus 4, right? And this polynomial has two real roots, right? We know that this polynomial has two real roots, right? Which certainly implies that so what does this imply? Right, so which implies by Rolle's theorem that if prime x, I mean fx, doesn't have five real roots. And why is this the case? Because if fx had five real roots, then this would mean, and we know that fx is a separable polynomial, right? So it means that the polynomial fx has only simple roots. All its roots are distinct roots. It has no repeated roots, or it has no multiple roots. All its roots are distinct. And Rolle's theorem says that between any two roots of fx there should be a root of f prime x, right? So technically there should be four. If fx has five real roots, then f prime x should have four real roots. But we just saw that this polynomial has exactly two real roots, right? Namely the fourth root of 4 by 5 and the negative of the fourth root of 4 by 5. The other two roots are actually complex roots, right? So if x cannot have so the polynomial, so I should write it properly. So fx doesn't have five real roots. It has either one real root or three real roots. Okay, and I mean, how should I say that one? Yeah, it really doesn't matter now. Okay, so yeah, hence fx has two complex roots or four complex roots. It actually has, I believe it actually has exactly two complex roots. That is all three. That is, it has three real roots and two complex roots. And to prove that it has three real roots, you can use the intermediate value theorem. Okay, so anyways, we don't need this much. So fx has either 2 complex roots or 4 complex roots, and hence if tau mapping c into c, which sends any z onto z bar, is the complex conjugation associated to C. Note that this is a field homomorphism of C into C. It is actually an automorphism of the object C, right? This complex conjugation, then tau restricted to E, which is actually equal to, what is E? We actually know what E is. E is a splitting field of the polynomial x square 5 minus 4x plus 2 over Q, right? So E is just Q adjoined with all the roots of this polynomial, right? Because we know by definition splitting fields are given like this, right? That this splitting fields, a splitting field of a polynomial is just the minimal extension of the base field in which the polynomial has all its roots, right? Counted with multiplicities, of course. That is over which the polynomial splits completely into a product of linear factors, right? Yeah. So tau restricted to E. Yeah, I should be very precise when I say all these things. Why is tau restricted to E? And that is also clear, right? Tau restricted to E belongs to the Galois group of E over Q as E over Q is Galois. We just saw it. So this is a sub extension. I mean yeah. Yeah, this I'm not totally correct here. We still need to figure out a few things. So E is Q adjoined with, yeah. So E is Q adjoined with the roots of this polynomial in E, right? And tau being the complex conjugation, if you restrict it to E, if you restrict it to the roots, it will just permute the roots, right? Because it's complex conjugation, and complex roots of a polynomial, of a real polynomial, always occur in conjugate pairs, right? So it will permute the roots, it will fix Q, right? Yeah, and hence this is yeah. As complex roots of fx are in conjugate pairs. So tau restricted to is an element of the Galois group of E over Q and is of order 2. Precisely because we have proved that this polynomial has at least 2 complex roots which are conjugates to each other, right? So this element is an element of order 2. Thus, so till now we only know these facts, okay? So till now we know, number 1, 5 divides the order of the Galois group of E over Q. Number 2, that the Galois group of E over Q has an element of order 2. Right? And number 3 is this, that since we have a separable polynomial of degree n, hence the Galois group of the polynomial, that is the Galois group of a splitting field of this polynomial, has to be a subgroup of Sn. Why? Because you can make the Galois group of E of the splitting field of this polynomial act on the set of roots of the polynomial, okay? It will just permute them, right? So there is a mapping of gal E over, of the Galois group of this polynomial into Sn, right? And this mapping, you can check, has to be, this is the permutation representation associated to the action, and this mapping has to be injective, right? It clearly should be injective. Okay. So yeah, because if some element of the Galois group fixes all the roots, right, then it has to fix, it should be the identity automorphism of the splitting field, right? Because the splitting field is the base field adjoined with the roots. An element of the Galois group always fixes the base field, and moreover we have assumed that it fixes all the roots as well, so it has to be the identity, right? So the Galois group of the polynomial should be a subgroup of Sn, and in this case, since the polynomial has 5 distinct roots, it's a separable polynomial. It's a separable polynomial of degree 5. Hence the Galois group of E over Q is a subgroup of S5. Okay, so 5 divides the order of the Galois group. The Galois group is a subgroup of S5, and the Galois group has an element of order 2. Okay, now any element, by Cauchy's theorem we know, yeah, by Cauchy's theorem gal E over Q has an element of order 5, which has to be a 5 cycle, because the only elements of order 5 in S5 are 5 cycles, which has to be a 5 cycle as the only elements of order 5 in S5 are 5 cycles, and the Galois group is a subgroup of S5, or it's isomorphic to a subgroup of S5, right? Thus this subgroup of S5 contains a 5 cycle. Yeah, we need to be placed, we need, this is why we need to show that it has 3 real roots. Yeah, so I should say, so yeah, so I'll just put this for you to check using, okay, so check that, just write this. Okay, so I need to make some space. Yeah, so check that fx has exactly 2 complex roots, and your hint is intermediate value theorem. So check that it has exactly 2 complex roots. Thus it contains a 5 cycle, and yeah, so the Galois group not only has an element of order 2, it does have a transposition. Okay, as a I should put this one at first at the beginning, so that everything is properly clear. Yeah, sorry about this, but yeah, I need to place it as first. So the Galois group of E over Q is a subgroup of S5, as gal E over Q acts faithfully on the 5 distinct roots of fx. This polynomial is a separable polynomial, right? So it will have exactly 5 distinct roots, and the Galois group acts faithfully on that set. Second is that gal E over Q has a 2 cycle. Third is gal E over Q, or third is 5 divides the order. Okay. So by Cauchy's theorem, gal E over Q has an element of order 5 which has to be a 5 cycle, as the only elements of order 5 in S5 are 5 cycles. Thus it contains a 5 cycle and a 2 cycle. It's a subgroup of S5 which contains a 5 cycle and a 2 cycle. And since S5 is generated by any 5 cycle, plus any 2 cycle, hence the Galois group of E over Q has to be isomorphic to S5 actually. Not a proper subgroup of S5 but actually the whole of S5. So this is isomorphic to S5. And now we are done. Okay. So again, if you have any questions, you can always ask me. You can always write to me. So let us move on to the next problem. Problem 6. Okay. So maybe we can do this one. So problem 6. So let K be equal to Q adjoined with the square root of 2, L be equal to Q adjoined with the square root of 3, and F be equal to just Q. Okay. So we need to choose all the correct options. Option A says that the degree of KL over K is equal to 4. Option B says that the degree of KL over L is equal to 4. Option C says that KL is actually equal to Q adjoined with square root of 2 plus square root of 3. And the fourth option says that K and L both are radical extensions of F. Now this is easy, this is not difficult at all. So we consider the solution. Okay, so just we quickly note that the composite term KL is just Q adjoined with square root 2 comma square root 3, right? Now A is not correct, as KL over K, the degree is 2 exactly. So KL over K is the degree of, the degree of KL over K is the degree of Q square root 2 comma square root 3 over Q square root 2, and root 3 satisfies the polynomial x square minus 3 over Q square root 2, and root 3 is not an element of Q square root of 2, which therefore implies that the degree has to be exactly 2. And option B is not correct again, as KL over L is again 2. What about option C? So we note that, so C is correct. We claim that C is correct. So C is correct, as Q square root of 2 comma square root of 3 contains q square root 2 plus square root 3. This is obvious because q square root of 2 comma square root of 3 contains root 2 plus root 3, and the smallest subfield of C, let's say, which contains both q and root 2 plus root 3 is q adjoined with root 2 plus root 3. So q adjoined with root 2 plus root 3 must be contained in this, and conversely q adjoined with root 2 plus root 3 contains 1 by root 2 plus root 3, which is equal to root 3 minus root 2, right? So contains 1 over this, right, which is root 3 minus root 2, and hence q adjoined with root 2 plus root 3 contains the root 2 plus root 3 minus root 2 minus, I mean root 2 plus root 3 minus of root 3 minus root 2, which is just root 3. So contains both, I mean twice root 3, and hence root 3 is also contained. So contains both root 3 and root 2, which implies q adjoined with root 2 plus root 3 is actually equal to q adjoined with root 2 comma root 3. So this we have jumped a step, maybe I'll write it fully. So this contains this, and so we have inclusions in both directions, which implies that they are equal. And option D is clearly correct. Why? So why is K a radical extension of Q? Because K is in fact a pure extension of Q, right, of type 2, because K is Q adjoined with root 2, and we know the square of root 2 is in Q, right? So K is actually a pure extension of Q of type 2. Similarly, L is again a pure extension of Q of type 2. So clearly we have so we have a radical tower of length 1, I should say, Q root 2 over Q. So Q root 2 is a radical extension of Q. K and L are in fact pure extensions. They are in fact pure extensions of Q of type 2. Okay, so that finishes this particular problem. So let us move on to the next problem. So let's look at problem 7. So what does problem 7 say? So maybe we can solve, let's say we'll solve this particular problem. So, so let's take this one. Let K is equal to Q adjoined with the fourth root of minus 1, and F is equal to Q, right? So we need to choose all the correct options. So option A says that K over F is a simple radical. K over F is a simple radical extension option B says that Q adjoined with square root of minus 2 is an intermediate field between K and F. Option C says that automorphism group of K over F is cyclic. And option D says that the degree of K over F is exactly equal to 2. Right. So let us solve this one. So we take, let's read it once again. So we take k to be equal to q adjoint with the fourth root of minus 1, right? So what is the fourth root of minus 1? Okay. So, and we take f to be q. So we need to first of all determine whether k over f is a simple radical extension. Certainly k over f is a simple extension, but is it a radical extension? That is, in fact, that is clearly true because it's a pure extension of type minus 1, right? I mean pure extension of type 4. So A is correct. As A is correct as k over f is in fact a pure extension of type 4. What about option B? Q square root of minus 2 is an intermediate field between k and f. Okay. So we need to figure out whether q square root of minus 2 is an intermediate field between k and f. So I'll give you 5 minutes, or maybe I'll give you 2 minutes to think about this, and then we can discuss. So q square root minus 2 is an intermediate field between k and f. Should this be correct or should this be not correct? So should square root of minus 2 be here or not? So B is correct actually. So you need to check this. This involves some computation, so I'm not doing it here. But a hint is a fourth root of minus 1 is a primitive or is it, I mean, yeah, fourth root of minus 1 is an nth root of unity. I mean, is an eighth root of unity. So that you already have a formula, and using that you can do this. Now automorphism of k over f yeah is a, yeah, I shouldn't say this, in fact is a primitive eighth root of unity. Yeah. So what k over f, since fourth root of minus 1 is a primitive eighth root of unity, hence what k over f comma being, I mean this, so k over f being the eighth cyclotomic extension implies, as we checked above, what K over F is isomorphic to Z8 cross, right? Which is not cyclic. So what is the order of Z8 cross? It's phi of 8. What is phi of 8? It is 8 times 1 minus half, which is 4, right? And why? And you can check that this is a abelian group of order 4. It's precisely Z2 cross Z2. Okay. So this Z4 cross is isomorphic to Z2 cross Z2, right? Which is not cyclic. And what about option D? K is to F has to be equal to 2. So this is what is being claimed in option D. That the degree of K over F is equal to 2. So K is Q adjoint with the fourth root of -1 and F is Q. We need to check whether the degree of K over F is 2 or not. So that the most natural thing to say here is that the degree should be 4, but we need to be very careful whether there is some polynomial over Q of degree 2 whose root is fourth root of -1 or not. So what do you think about this? Should this be the case or not? So one way to do this is to look at the polynomial x to the power 4 plus 1, which has fourth root of -1 as a root, and you can check, or you can try to see whether this polynomial is irreducible or not. Okay, but here you can't apply the Eisenstein's criteria for sure, but you need to figure out whether this is the case or not. Okay, but a much simpler way to do this is to use the fact that K over F is the 8th cyclotomic extension, right? And we know that the degree of the 8th cyclotomic extension is just equal to phi of 8, which is 4, as K over F is the 8th cyclotomic extension. Over Q. Over Q. Yeah. Since it's the 8th cyclotomic extension over Q, hence K over F, yeah, so the degree has to be phi of 8, which is 4. So certainly option D is incorrect, option C is incorrect, option A and option B are both correct. So this is wrong, this is wrong, this is correct, this is correct. Yeah, I should also mark the options here. So option A was incorrect, option B was incorrect, option C was correct, and option D was correct. Yeah. So this is what finishes problem 7. We still have some time. We'll be doing a few more problems depending on how much time we have. So let's do one problem. So let's see. So let's look at this problem. Let K be equal to Q adjoint with omega, L be equal to Q adjoint with the fifth cube root of 5, and let F be equal to Q, where omega is equal to e to the power 2 pi I over 3. Okay, we need to choose all the correct options. Oops, sorry again. Yeah, so So where omega is equal to e to the power 2 pi I over 3. So we need to choose all the correct options. So option A says that KL over L is Galois. Option B says that ought KL over L is isomorphic to ought L over F. Option C says that ought KL over L is isomorphic to ought K over F. And option D says that L over F is Galois. Okay, so let's solve this. So K is Q adjoint with the primitive cube root of unity. L is Q adjoint with the real cube root of 5. F is taken to be Q. Okay. Now KL over L is Galois or not, we need to figure this out. Now we know that the composite term KL is just Q adjoint with this and omega, right? And this is the splitting field over Q of the separable polynomial, right? Separable polynomial. Yeah, we can in fact do better. We don't need to look at Q. Do we? No, we don't need to look at Q because, yeah. Yeah. So splitting field over L, Q adjoint with cube root of 5 of the separable polynomial x cube minus 5 belonging to qx, right? The roots of this polynomial are cube root of 5 omega, cube root of 5 omega square, and the splitting field will be of the form, the splitting field exactly looks like q adjoint with cube root of 5 comma cube root of 5 omega comma cube root of 5 omega square. Okay, and this is equal to q adjoint with cube root of 5 comma omega, right? You can easily check this. So the q adjoint with cube root of 5 comma omega is the splitting field. Yes, I'm sorry, I'm sort of, my mind is in a different place right now. So what I want to say is q adjoint with cube root of 5 adjoint with omega is the splitting field over q adjoint with cube root of 5 of this polynomial x cube minus 5. Yeah. Of this polynomial x cube minus 5 belonging to q adjoint with cube root of 5x, right? Yeah. You just keep on adjoining roots and nothing else. Yeah. To the base field to get the splitting field. So this is a separable polynomial. You have a splitting field of a separable polynomial. So this is Galois. Hence, KL over L is Galois. Thus A is correct. Correct. Okay. Now what about the case of, okay, so note that, so we note that L over F, so L is equal to we note that K over F, K equal to q omega is the splitting field of the separable polynomial x square plus x plus 1 in qx, so that k over f is Galois. Now also note that the polynomial x cube minus 5 is an irreducible polynomial, right? So also note that this polynomial so note that x cube minus 5, the polynomial x cube minus 5 is an irreducible polynomial over q that has a root in the extension L equal to q adjoined with cube root of 5, which is a subfield of R, but not all its roots. But not all its roots in L, right? So the point is that L over F cannot be a normal extension. Why? Because if it, so a normal E over F is said to be a normal extension if and only if every, so an extension E over F is said to be a normal extension if and only if it is an algebraic extension and every irreducible polynomial over the base field F that has a root in E splits completely over E into a product of linear factors, right? That is, every irreducible polynomial over F that has a root in E has all its roots in E, or splits completely over E into a product of linear factors. Okay. But this is not clearly the case with L over F here, because x cube minus 5 is again an irreducible polynomial over the base field that has a root in this extension, but not all its roots are in this extension. That is, this polynomial doesn't split completely or factor completely into a product of linear factors. Okay, it doesn't split completely or it doesn't factor completely into a product of linear factors over L, but it has a root in L. Hence, L over F is not normal, is not a normal extension, and hence not Galois. So certainly option D is incorrect. D is not correct. Okay, so we have K over F is Galois, L over F is not Galois. Okay, L over F is just an arbitrary extension, and therefore we do know that if we take the Galois extension K over F and if we slide it along L over F, so that we arrive at KL over L. Okay, then this has to be a Galois extension. Hence, okay, so since K over F is Galois, hence KL over L so since K over F is Galois, hence KL over L is Galois, and automorphism group of KL over L is isomorphic to automorphism group of K over K intersection L, right, which is a subgroup of automorphism group of K over F, right. We need to figure out whether this is actually isomorphic to automorphism group of K over F. So automorphism group of K over F, K over F is a Galois extension, K is Q omega, the degree of this extension is 2, okay, and hence the order of the Galois group is 2, so the Galois group is precisely Z2, okay, and what is the automorphism group of KL over L? KL over L is again a Galois extension, right? And this is it's a Galois extension of order 2, so its automorphism group has to be degree 2. Okay. So we don't, we sort of don't need this last two lines. Okay. What we have is what KL over L. So KL over L is a Galois extension. This is important, or this is needed. Okay, and odd KL over L will, the coordinate of odd KL over L will be equal to the degree of the extension KL over L, which is exactly equal to 2. Okay, and so this is isomorphic to Z2, which is isomorphic to odd K over F, right? Hence C is correct. Okay, but option B is not correct. Why is B not correct? As any sigma in the Galois group of L over F, okay. What is L? L is Q adjoint with the cube root of 5, right? Now you take any sigma in the Galois group of L over F, so it is an automorphism of Q adjoint with cube root of 5, which fixes Q. Okay. Now since cube root of 5 is a root of the polynomial x cube minus 5 over Q, so sigma permutes the roots of this polynomial, right? So sigma can map cube root of 5 to either cube root of 5, or it can map it to cube root of 5 omega, or it can map it to cube root of 5 omega square. But cube root of 5 omega and cube root of 5 omega square are not inside L, right? And since sigma, the image of sigma must be equal to L, so sigma of cube root of 5, I mean L is the codomain of sigma, right? So the image should be contained in L. So sigma adjoint with cube root of, I mean sigma of cube root of 5 must be in L. So sigma of cube root of 5 has to be cube root of 5. Must fix cube root of 5 so that the automorphism group of L over F, or Galois group of L over F. I use two different notations here. Yeah, you should write hot. Automorphism group of L over F is isomorphic to the trivial group. Okay. So B is certainly not correct. The degree of the, yeah. Okay, so which of these are correct? A is clearly correct. Okay, so I sort of wrote it again. Okay, never mind. I sort of did the fact that it's Galois twice. We don't need this, but yeah, okay. So A is correct, B is not correct, C is correct, D is correct. Sorry, D is also not correct. C was correct, right? Yeah, B is not correct. Okay, so yeah, I guess this finishes problem 8 as well. And this is sort of the end of our discussion. We have almost reached time. So, what I want to say is if you have any questions, you can always feel free to ask me. And please do write to me. And I do hope that you are attending Ajay Prajapati's session. And yeah, if you have any questions regarding today's session, please do write to me. So we solved 8 problems.